we're going to move straight into uniform rotational motion. And here's a bit of an overview. We're going to look at angular motion now instead of linear motion. And when we talked about linear motion, we started off by defining displacement, which was our change in position with time. Now our displacement may actually be defined in terms of radians or degrees. The majority of calculations we're going to do will use radians, so we'll cover the use of radians and how to convert to them. We'll look at angular displacement, and then of course the change in angular displacement with time being the angular speed or velocity. We can then look at the change in that speed being the angular or centripetal acceleration that we'll get. So there'll be an angular acceleration, a centripetal acceleration, and there may actually also be a linear acceleration mixed in. So we do have to watch our velocities and accelerations in this particular module. We'll also talk about the difference between a centripetal and a centrifugal force. So as we said previously, we've looked at this. Cast your mind back to when we dealt with our initial values in terms of vectors. Here we're dealing with a straight line velocity vector. Everything was nice and linear. Maybe things acted at 90 degrees occasionally, or we had to invoke a sine or cosine in order to explain our forces. But the vectors themselves were always linear in every case. Now the only difference that we're looking at here is the circular cases. And remember, Newton's laws will always apply. It doesn't matter if we're dealing with circular cases, it doesn't matter if we're dealing with linear cases. Newton's laws are still in effect. So where can we actually apply the circular case of Newton's laws? Well, Ferris wheels are one. The rotating drum of a washing machine. Helicopters, little more exciting than washing machines. And a helicopter is a great example. That if you think about a helicopter in terms of angular and physical displacement, and then look at the blades. So take this blade and think about the angular displacement here. Every single point along this blade will have the same angular displacement. It'll go the same number of radians or the same number of degrees per second. But if you're standing out on this edge, you might go kilometers in terms of the distance this blade turns. If you're standing in the center, you're still turning the same number of degrees, but you'd just be spinning around and not going anywhere in terms of meters. So there is a bit of a disconnect between the physical displacement in meters and the angular displacement in radians or degrees that we're going to look at. It also dictates how a car stays on a track while it's taking a curve. This vehicle will throw itself into this curve. It will feel linear forces from either side, but it'll also feel a centripetal acceleration towards the center of this curve, which will indicate how it moves. Nunchuckers, of course. Go and buy a pair of nunchuckers, spin them around, hit yourself over the head, nobody cares. But the moment you hit your brother with them, you get confiscated. And of course, the same physics that dictates how martial arts weapons that you spin around a chain work also applies to such lofty things as the motion of the planets. So let's take a look at this situation. If we take an object and we spin it in a circle, and here we're dealing with a perfect circle, so our radius will stay the same for the object's entire motion. Here's the center of the circle, and here is that radius. Our object is going to start out on this x-axis and then be spun through some angle, delta theta. The radius is here staying the same. Our angle here, our displacement, can be defined in terms of radians or indeed degrees. This is not a physical displacement. This is an angular displacement. And it does not matter where you are in terms of the radius along, say, this string with this ball on the end. It doesn't matter at what point you're at along this string. Theta or delta theta that is rotated through will remain the same. S, however, the physical displacement, will change. So delta S1 here is not equal to delta S2. the object here has gone much further than if it were located at a smaller radius. So the displacement in meters can change based on your radius. The displacement in angular terms will remain the same for any radius. And this should be true of anyone who's run on a track. You really want to be the guy on the inside of that track, not the guy on the outside, because if you're on the inside, you're not running as far as the guy on the outside. So when we are looking at our movement around this circle, this is the same diagram as in the previous slide, we have to look at r, which is our radius of curvature. We'll have a rotational angle, an angle with which we moved, which is our angular displacement, which is delta theta, and a path displacement, that's sometimes referred to as an arc displacement, which is going to be delta s. And that's the actual distance in meters that you're traveling in your circular path. So delta theta at r equals 0 is the same delta theta at r equals r. But delta s1 is not equal to delta s2 for the same delta theta. That means we can convert between a delta theta, an angular displacement, and a physical displacement, delta s, by invoking the radius. So delta theta here is delta s over r. And that's how we take a path displacement, delta s, and relate it to an angular displacement, delta theta. Now for all of our calculations, we will keep our arc length units in radians. So for a complete revolution, as we go completely around in this circle, we will end up with the arc length equaling the circumference. The circumference here will be 2 pi r. So delta theta essentially winds up being 2 pi r over r. And that will cancel out your r values. And that means that for one whole rotation, your object will have moved 2 pi radians. So instead of 360 degrees, we'll go 2 pi radians for one whole revolution. So you can see different definitions for revolutions in this class. You might have something described in revolutions, and engineers love to talk about RPM, revolutions per minute, and sometimes you might have to convert that to radians per second in order to make sense in this class. So one revolution of this particular wheel will be 360 degrees or 2 pi radians. So if delta theta is 2 pi, one revolution has been completed. If delta theta is 4 pi, your object has gone 2 revolutions. If your object has moved pi, then it's gone half a revolution. So that means 2 pi radians is 360 degrees. That means we have a conversion factor now that 1 radian is equal to 360 degrees divided by 2 pi, which gives us 57.3 degrees. Quite frequently you're going to want to convert between radians and degrees. And degrees is basically 180 over pi radians, and radians is pi over 180 degrees. So if you're going from radians to degrees or degrees to radians, you can easily convert between the two. Definitely make sure you're familiar with how to do this. So converting 240 degrees into radians or 90 degrees into radians, or sometimes fractions of a rotation, or converting 0.393, the decimal version, in radians to degrees. Some people like to express their rotations in terms of fractions of pi. So sometimes you'll see pi over 3 in terms of angular distance. I tend to reduce it down to some kind of decimal. It just makes life easier in terms of calculations. I'm not really bothered if you express things this way or this way. But be aware, in assessments, I will probably use the decimal. So if we're just looking at those conversions, here's our 240 degrees, converting them into radians, we're really going to say 240 times pi over 180, and that'll give us about 4 radians. converting 90 degrees, 90 times pi over 180 will give us 1.57 radians. Pi over 3, 60 degrees, 0.393 radians will give us 22.5 degrees. So have an idea of the kind of numbers you should expect to see from these conversions. Let's take a look at this in terms of a problem. Here we've got a rope. It's wrapped several times around a drum of radius 50 centimeters. How many revolutions of the drum are required to raise the bucket a height of 20 meters? So this bucket is sitting here on the surface and we want to raise it 20 meters up. This rope is wrapped around the drum, so how many times do we need to turn this drum in order to get 20 meters of height out of this oddly shaped bucket? Well, theta is s over r. S is 20 meters, that's our linear displacement. And r is 0.5 meters. Remember, this is 50 centimeters. So theta is s over r, that's 20 over 0.5, which will give us a theta of 40 radians. Now, the question specifically asked how many revolutions of the drum are required. We got 40 radians. So now we have to take our radians, say 1 revolution is 2 pi radians, and say 40 times 1 over 2 pi will give us 6.37 revolutions, or 6.4-ish times we would have to turn this drum in order to lift our bucket 20 meters. Now remember, if you look at theta here, you'll end up in revolutions because the radians will cancel. You've got 40 radians over 2 pi radians. That gives you no units at all. So the revolutions is terms of how many times you're turning something. Physically, these units have gone away. Here's where we want to define another velocity. So velocity v is still our linear velocity, and you might see that in some contexts here. But the angular velocity, omega, is a measure of how fast an object is rotating, or the rate of angular change. And so this means omega is delta theta, how many radians we're turning through, divided by delta t. So theta over t, radians per second. And remember, this velocity is defined as radians per second. Don't mix up your velocities. There's a lot of different terms coming around now, some linear, some angular, and you need to pay attention to the question to decide which is it giving me, or which does it ask for. So when we are spinning something around, the angular velocity is actually a constantly changing linear velocity. This wheel at the bottom here will have an omega that is in this direction in terms of its rotation of this wheel, but there'll also be a linear velocity at every point on this wheel, v, coming off. In this case, there's also a translational velocity of the whole wheel, which could also be v, usually given as little vt, which can still be confusing since this is a tangential velocity, which could be vt. So if we look at the velocity of a point on the wheel, v is going to be delta s by delta t. Now s was equal to r times theta. So if we substitute in for s, into our first equation, v is equal to r delta theta over delta t. Remember from earlier, omega was delta theta by delta t. Substitute in here, and we can say now that v is r times omega. So the velocity of any point on the wheel in a linear sense becomes omega times r. So omega is v over r in radians per second. And that should make sense since radians are sort of an arbitrary choice that we made in order to calculate and discuss angular change, an angular measure. So radians, essentially, we divided the circle up into little units of our choice. So if you think about this is meters per second, this is meters, we'll end up with per second. We're referring to it as radians per second, just for simplicity. So looking at angular velocity, the rate of angular change of angular displacement, omega, is delta theta by delta t. Later on especially, we can talk about the frequency, how many times something rotates. And we can say that omega can also be 2 pi, this is how many times your object has gone around in once, how many times it rotated, multiplied by how many times it's gone down. 2 pi times f. How many times has it gone round? The thing to remember in all of our calculations when we're dealing with angular measure, or especially when we're dealing with angular velocity, use radians in all your calculations. If you use degrees with omega, you will get the wrong answer. Angular velocity, always quote in radians. Let's take a look at another one. So here we've got a rope wrapped several times around a drum. We have the radius of the drum of 20 centimeters. What's the angular velocity of the drum if it lifts the bucket to 10 meters in 5 seconds? So how quickly does this thing have to rotate to lift a bucket 10 meters in 5 seconds? So theta, this is the angle that it's moved through, is s over r. We know this linear distance is 10 meters. That's how far this will have to have rotated. So s over r is 10 over 0.2, which will give us 50 radians. This wasn't the question. The question is, what's the angular velocity? What's the omega of this system? Well, the omega of this system is delta theta over delta t, or 50 radians over 5 seconds, giving us an omega of 10 radians per second. So when we are talking about angular and linear speeds, we can take our definition of angular displacement and say that v is delta s by delta t. That means we have delta theta times r by delta t, because s is theta r. This will cancel here. This will become delta theta by delta t. Take the r out here, factor this out. This means v is omega r. So let's take a look at v and omega. The v we're talking about is a linear velocity, a linear speed of any point on this disk. And that linear speed is tangential. It's in this direction coming off of this object. So b here will have a linear speed that's constantly changing direction. So here, what's the final linear speed at points A and B on a flat rotating disk? So here we've got a disk and it's spinning around, and we've got two objects, A and object B, sitting on this disk. One sitting at a radius of 20 centimeters and B is sitting at a radius of 40 centimeters. They will both be experiencing a velocity in omega and a velocity in v in a straight line. So let's figure out the velocity of the object sitting at 20 centimeters. V will be omega times r1, which is 20 radians per second times 0.2. That'll give us a velocity of 4 meters per second. Let's do the same for object B. So object B now will be omega times r2 essentially. Apologize for that little flub there. 20 times 0.4, which will give us 8 meters per second. So in both of these cases, both of these objects will have the same omega value. They'll have the same value of rotational velocity, of angular velocity of 20 radians per second. But if we look at their linear velocity, it will change based on their radius along this object. So we have v equals omega r, and that's our linear versus our angular velocity. We can also then say that v is delta v by delta t here, which is going to be delta v by r times r over delta t, which becomes delta v over delta t r. That means acceleration, in our case, will end up being this alpha times r. this alpha here is an angular acceleration. This a is a linear acceleration. And so the angular acceleration is defined as the rate of change in the angular velocity in radians per second per second. And that is alpha. And this is one of those things to really watch out for. Now we have linear accelerations, angular accelerations, linear velocities, and angular velocities. And you must always read a question carefully to decide which one you're being asked to find. And it's a very common error for people to find an angular velocity or acceleration when they were looking for a linear one. You can also find the angular acceleration from the change in frequency, and things like this we'll see more nearer the end when we start talking about oscillations. But please keep these in mind, that the angular frequency can also be 2 pi times f divided by t, since omega is 2 pi f. So looking at our angular versus our linear parameters, a is delta v by delta t. A is also alpha r, and v is omega r. That means we could write this as A is Vf minus V0 over t to become alpha r is r omega f minus r omega 0 over t. So the angular acceleration is the time rate of change of our angular velocity. R omega is simply going to be this. Alpha, these r's are going to cancel out and give you alpha in terms of omega and t only. And this is very convenient, because what it turns out is that all of those equations of motion, and apologies to people who thought they could forget the equations of motion and move on, here they are again, they're coming back. But now, instead of being in linear terms, in terms of s and v and a, they're now in terms of theta, omega, and alpha. These are these rotational versions of the same equations of motion that you've always seen. So Newtonian physics works in the circular as much as it works in the linear, and all of our equations of motion found through calculus still apply. So let's take a look at another problem. Here we've got a drum. It's rotating clockwise at 100 RPM. So here we're looking at a problem in revolutions per minute. It's undergoing a constant counterclockwise acceleration of 3 radians per second for 2 seconds. So the drum is rotating one direction, and then the alpha, the acceleration, is applied in the other. So essentially this is a brake which is trying to slow down or decelerate the rotation of this object. We have an omega. We're going to say it's negative 100 RPM. So the general consensus is that it's negative if it's going clockwise, and it's positive if it's going counterclockwise. This is an arbitrary decision that people make. That's sort of the convention. I'm not as concerned as long as you define whether you're talking about clockwise or counterclockwise as your positive or your negative. I tend to just write the magnitude of, 3 radians per second, and then just write clockwise or counterclockwise next to it. Additionally, apologies if I ever say anti-clockwise. That's the English version of counterclockwise. But anyway, back to what we're talking about. That's the angular displacement. So our initial omega is 100 RPM. We've defined it as negative 100 RPM. Here we are applying an acceleration of 3 radians per second for 2 seconds. What's the angular displacement? Well, take our 100 RPM, that means revolutions per minute. That's the convention, that's the way it's written. So revs per minute. We're going to divide by 60 to get it into seconds. We're going to multiply by 2 pi to get it into radians. So 100 times 2 pi over 60 gives you your radians per second here. And that'll give us 10.5 radians per second. Now let's apply an equation of motion. We've got alpha, we've got t, we've got omega. So now we can say theta, the distance this thing will rotate in terms of the angle, will be omega t plus half alpha t squared. So this will be negative 10.5 here because we had to convert this. This is revolutions. Here's our 10.5. So negative 10.5 times 2 plus 1/2 3 radians per second. I know it says 2 here. Times 2 squared. That means theta will wind up giving us negative 20.9 radians plus another 6. So theta is negative 14.9 radians. That's how far this drum will move after the acceleration is applied. The net displacement is still in a clockwise, is still in the same direction. It's still going to be negative. It's still going to be clockwise. Let's take a look at another one. If the block is lifted from rest here until the angular velocity of the drum is 16 radians per second after 4 seconds, what's the average angular acceleration of our system? So now we have a block lifted up, and it's going to be lifted until omega is 16 radians per second. This is after 4 seconds, and it wants the angular acceleration. Here we've got a height of 20 meters. Alpha is going to be omega f minus omega I over t, essentially the way we'd used to do A, delta v over delta t, here delta omega over delta t. Omega I, our initial omega, is 0, or alpha is omega f over t. That gives us 16 radians per second over 4 seconds, which gives us an alpha of 4 radians per second per second. Not a particularly complicated one here. Let's take another one. Lots of examples. So what's the average angular and linear acceleration at point B on this disk? So we're dealing with point B, which from our previous slide was this one at 40 centimeters. Omega here was 0, omega f was 20 radians per second, R2 is 40 centimeters, that's point B, and t is 4 seconds here. Well, alpha is delta omega by delta t. That's 20 radians per second over 4 seconds. So alpha will give us 5 radians per second per second. Our linear acceleration here, the second part, is going to be A, which is going to be alpha r. So take your alpha, take your circular acceleration, and then just multiply it by the radius. So the same as when we looked at velocity. V was omega r. If we're looking at linear acceleration, A is alpha r. See the connection? If we multiply by the radius, our angular values become linear values. That means an alpha of about 5 radians per second corresponds to an A of about 2 meters per second per second. So we can keep applying our equations of motion. So if we take a disk here, r is 50 centimeters now, and it's rotating at 600 revolutions per minute, and comes to a stop after making 50 revolutions. What's our acceleration? Omega here is 600 RPM. Omega f is 0 RPM. So it comes to a stop. So we're going from 600 RPM down to 0. It also rotates 50 revolutions in that time. So theta is equal to 50. Select your equation. So the same selection criteria we've always had when we dealt with the linear case. We know that one of these is 0 anyway, so this is going to go away. We've got 2 alpha theta is equal to omega I squared. Convert. Remember to convert. 600 RPM, 2 pi, 60 seconds. 2 pi radians over 60 will give you 62.8 radians per second. 50 revolutions, however, is 314 radians. So alpha here is going to be whatever our original omega was squared divided by 2 theta. Theta, the total revolution, is not just 50, but 50 times pi, essentially, 2 pi. So we're in with 314 radians for 50 revolutions. So here, alpha is 62.8 squared over 2 times 314. That will give us negative 6.29 meters per second, radians per second per second.